Good day, class, and welcome to yet another lesson in organic chemistry. In our previous lessons, we started with hydrocarbons, and we also started with one class of hydrocarbons, that is aliphatic hydrocarbons. And so far, we've treated alkanes as one of the aliphatic hydrocarbons. We started treating alkenes in our last lesson, and we said alkenes have a general molecular formula, CnH2n. We also went further to say alkenes are unsaturated carbons, and all the carbons are sp3 hybridized and are attached to each other by one sigma bond and one pi bond. We said the pi electrons of these double bonds are much more exposed than those of the sigma bonds. And as such, as they are more exposed than the sigma bonds, they tend to be more vulnerable to any attacking species. Which means that for alkenes to undergo any reaction, and we note that we said in our previous lessons that alkenes undergo mostly addition reactions. And as such, during these reactions, the pi bonds tend to react faster than the sigma bonds. We also went further to say alkenes are generally more reactive than alkanes, and this is so due to the presence of the carbon-to-carbon double bond. We did isomerism in alkenes, where we said alkenes undergo mainly two types of isomerism, that is structural and stereoisomerisms. We saw some examples, and we went further to look at the preparation of alkenes, and we said from the industry, alkenes can be obtained industrially by cracking of higher petroleum fractions. And from the laboratory, alkenes can be obtained by dehydration of alcohols. And dehydration of alcohols, how does it take place? It takes place in the presence of concentrated sulfuric acid and at 180 degrees Celsius, leading us to our alkene, and water is being produced. This dehydration reaction using concentrated sulfuric acid at 180 degrees Celsius is known as complete dehydration. Another dehydration is by passing a vapor of alcohol over hot aluminum oxide catalyst at 350 degrees Celsius. This is an incomplete dehydration. Another method by which we obtain alkenes from the laboratory is by dehydrohalogenation of halogenoalkanes, and this takes place in the presence of concentrated potassium hydroxide and alcohol, and it is being refluxed. We also saw the physical properties of alkenes, where we said alkenes are insoluble in water but soluble in organic solvents. The first three members, just like alkanes, are gases, and carbon 5 to carbon 15 are liquids, while above carbon 15 are solids, and all these change in temperature and all this change in state takes place at room temperature. We said their boiling points are slightly lower than those of their corresponding alkanes. We went further to see the reactions of alkenes, and we realized that it's due to the presence of the pi electrons. The reactions of alkenes are characterized by electrophilic addition across the double bond. And we saw the first type there. We saw addition of bromine water or chlorine water. We saw the addition of halogens. We also went further. We saw the addition of sulfuric acid. And in our lesson for today, we are going to continue with the reactions of alkenes. And the first one we'll be looking at is going to be reaction with acidified potassium permanganate. Like I said, the first one we're going to look at is reaction with acidified potassium permanganate. Alkenes react with acidified potassium permanganate and readily decolorize the purple color of potassium permanganate, forming a diol. This yields a diol. As you can see from the reaction there, we have ethene in the presence of permanganate and an acid is going to yield us a diol. The product formed immediately after that is going to hydrolyze in the presence of water to give us a diol. As you can see there, the end product is ethane 1,2-diol. And we're going to see that the reaction of halogenoalkanes hydroxylation can also be carried out by hydrogen peroxide. And this hydrogen peroxide is being used in the presence of osmium tetraoxide as catalyst. As you can see from the example there, we have our ethene plus hydrogen peroxide in the presence of osmium tetraoxide is going to give us ethane 1,2-diol. The next one we're going to look at, the next reaction of alkenes is addition of hydrogen halides. In this addition of hydrogen halides, you see that it is being determined by Markovnikov's rule. Addition of hydrogen halides. It is being determined by Markovnikov's rule. And what is this Markovnikov's rule? What does it state? Markovnikov's rule states that in the addition of a hydrogen halide to a carbon-to-carbon double bond in an unsymmetric alkene, the hydrogen atom attaches itself to the carbon atom linked with the largest number of hydrogen atoms. As we go further, you understand better. Alkenes react with hydrogen halides at RTP, forming alkyl halides. That's halogenoalkanes. For example, you see the example there. Ethene plus hydrogen bromide at room temperature, that is at RTP, is going to give us what? 2-bromoethane. An unsymmetric alkene. An unsymmetric alkene, what can you tell me an unsymmetric alkene is? An unsymmetric alkene is an alkene with different number of hydrogen atoms across the double bonds. We say an alkene is unsymmetric when this alkene has different number of hydrogen atoms across the double bond. That is, an unsymmetric alkene is an alkene with different number of hydrogen atoms across the double bond. As you can see from the example there, we realize that the first compound, after the double bond, the first carbon on the first compound has 2 hydrogen atoms. The second carbon atom has 1 hydrogen atom. That is an unsymmetric alkene, because we say an unsymmetric alkene is an alkene with different number of hydrogen atoms across the double bonds. Now, you look at the next compound there, the next alkene compound, you realize that it has a double bond on the first carbon atom, counting from the left. There's a double bond between carbon 1 and carbon 2. And this carbon 1 has 2 methyl groups attached to it. And as such, it has no hydrogen atom attached to it. Meanwhile, the second carbon atom has 1 hydrogen atom, thus making these 2 compounds an unsymmetric alkene. A symmetric alkene is an alkene with same number of hydrogen atoms across the double bond. A symmetric alkene is an alkene with same number of hydrogen atoms across the double bond. Like you can see from the board, you see that ethene across the double bond has 2 hydrogen atoms each attached to the carbon atoms. And the next compound there is butene. Across the double bonds, you find that each of the carbon atoms across the double bonds have 1 hydrogen atom attached to it, thus making it a symmetric alkene. And we said that addition of hydrogen halides to alkenes is determined by Markovnikov's rule. Markovnikov's rule states that in the addition of a hydrogen halide to a carbon-to-carbon double bond in an unsymmetric alkene, the hydrogen atom attaches itself to the carbon atom linked with the largest number of hydrogen atoms. Let's look at the example there. We have propene reacting with hydrogen chloride. Realize that when this hydrogen chloride is being hydrolyzed, we're going to have a hydrogen ion as a positive and a chloride ion as a negative. Thus, the arrow moves from the multiple bond to the hydrogen ion, Like you can see there, a carbocation is formed. When this carbocation is formed, you realize that the arrow moves now from the negative chloride ion to the carbocation, the positive carbocation, forming a 2-chloropropane. The next reaction we're going to look at is oxonolysis, that is determination of structure. If oxone is boiled through a solution of alkene, in an organic solvent such as tetrachloromethane, an oxonide is formed. What we mean here is, if oxone is boiled through a solution of alkene in an organic solvent like tetrachloromethane, like you can see, this is a tetrachloromethane there, it's going to yield us an oxonide. The first compound produced is an oxonide. And when this oxonide, how can you hydrolyze this oxonide? This oxonide can be hydrolyzed using water or zinc dust and ethanoic acid to form carbonyl compounds. Carbonyl compounds are aldehydes and ketones. It's going to form carbonyl compounds and hydrogen peroxide. To avoid the oxidation of the carbonyl compounds by the hydrogen peroxide, zinc dust is added, which reduces the hydrogen peroxide to water. You can see from my reaction there, you have propene reacting in the presence of oxone. We say oxone is boiled through a solution of alkene. In this case, the alkene here is propene, and this reaction takes place in an organic solvent. And the first compound formed is an oxonide. When this oxonide is formed, this oxonide can also be hydrolyzed, and can be hydrolyzed using water or zinc dust and ethanoic acid to form carbonyl compounds. Like you can see there, these are the carbonyl compounds. You see that ethanol is an aldehyde. Methanol is also an aldehyde. Now we go further to see how we said When this zinc dust is used to avoid the oxidation of the carbonyl compounds by hydrogen peroxide. And you can see how this zinc dust works. Hydrogen peroxide is being reacted with zinc dust. In the reaction, is going to form zinc oxide and water. It reduces the hydrogen peroxide to water. Thus, the hydrogen peroxide can't oxidize the carbonyl compounds. The next reaction we're going to look at is hydrogenation, that is reduction reaction. A mixture of hydrogen and an alkene passed over finely divided platinum or palladium catalyst without heating, that is at room temperature, or passed over finely divided nickel at 140 degrees Celsius produces an alkane. So you can see ethene plus hydrogen in the presence of platinum or palladium catalyst at RTP is going to yield us ethane. Ethene plus hydrogen in the presence of nickel catalyst at 140 degrees Celsius yields us ethane. The next reaction we're going to look at is reaction with oxygen or air. Alkenes burn in air with a luminous smoky flame to produce carbon dioxide and water. In the presence of silver catalyst, ethane reacts with oxygen to form epoxyethane, which can be hydrolyzed to give ethane 1,2-diol. Like you can see there, you see that where we say in the presence of silver catalyst, ethene reacts with oxygen. We say in the presence of silver catalyst, ethene reacts with oxygen to form epoxyethane, which can be hydrolyzed to give ethane 1,2-diol. Look for my reactions. Generally, we said alkenes react with oxygen, they burn in oxygen with a luminous smoky flame to produce carbon dioxide gas and water gas only. And now, we also said if silver catalyst is being used, the reaction of ethane with oxygen is going to yield an epoxyethane. And this epoxyethane can be hydrolyzed. Using water at 300 degrees Celsius to yield us a diol, that is ethane 1,2-diol. The next reaction we're going to look at is reaction with alkenes. That's reaction with other alkenes. Reaction with other hydrocarbons. Alkenes add across the double bonds in the presence of an acid catalyst to form higher alkenes. Typical example of this reaction is the synthesis of ethylbenzene. As you can see there, we have ethene plus benzene. The presence of an acid catalyst. The acid catalyst used there is aluminium trichloride, and at 100 degrees Celsius is going to yield us ethylbenzene. And a general reaction there, we have a general reaction of alkenes reacting with alkenes is going to yield us also ethyl alkene. Let's look at this. We have ethene reacting with an alkane, an unknown alkane. ROH refers to alkenes. In the presence of an acid catalyst, that's hydrogen ion, is going to give us an ethyl alkane. The next reaction there is going to be polymerization. Polymerization is a process whereby simple molecules, these simple molecules are called monomers. Polymerization is a process whereby simple molecules called monomers join together to form very large complex molecules called polymers. Simple alkenes undergo addition polymerization to form addition polymers in which there is neither gain nor loss of material. Like you can see from the reaction there, we have ethene in the presence of oxygen and at 1500 degrees Celsius and 200 atmosphere is going to give us polyethylene or polyethylene. Polyethylene is a normal plastic you use when you buy something from the store. You tie it in a wrapper. That's how you popularly call it, a wrapper. That wrapper in chemistry is polyethylene, and that is how it is being obtained, like you can see on your screen. The next reaction there, we also find chloroethane reacting, also undergoing polymerization to give us polyvinyl chloride or polychloroethane. The next thing we're going to look at is alkynes. Alkynes is another class of aliphatic hydrocarbons. So far we've treated aliphatic hydrocarbons. We did alkenes like that we just finished now, and the next one and the last hydrocarbon, the last aliphatic hydrocarbon we're getting into is alkynes. Alkynes are unsaturated hydrocarbons, and they have triple bonds between carbon atoms. Alkynes have the general molecular formula CnH2n minus 2. Like you can see, so far we've been looking at the reactions of all these and the physical properties of all these aliphatic hydrocarbons. And now we are going to look at the various molecular formulas of the compounds we've been treating, of the homologous series we've been treating. You have CnH2n plus 2. This one stands for alkanes. And CnH2n stands for alkenes. CnH2n minus 2 stands for alkynes. Alkanes have single bonds between carbon atoms. Alkenes have double bonds. Alkynes have triple bonds. Also, we're going to see that the unsaturated carbon in alkynes is sp3 hybridized. Those of alkanes, the carbon atoms in alkanes are sp3 hybridized. The carbon atoms of alkenes are sp2 hybridized. Meanwhile, the carbon atoms of alkynes are sp hybridized. The unsaturated carbon is sp hybridized, comprising of 1 sigma bond and 2 pi bonds. The hybrid orbitals are as far apart as possible, with bond angles of 180 degrees Celsius, giving the alkynes a linear shape. Alkynes are the most reactive among the aliphatic hydrocarbons. Alkynes are the most reactive due to their high electron density as a result of their pi electrons. Alkynes form a homologous series of unsaturated hydrocarbons with carbon-to-carbon triple bonds. They have a general molecular formula, CnH2n-2. The unsaturated carbon is sp hybridized, comprising of 1 sigma bond and 2 pi bonds. The hybrid orbitals are far apart as possible, with bond angles of 180 degrees, giving them a linear shape. For example, we have the example below there. You see that from the example below there is 2 carbon, and this gives rise to ethine, and the bond angle of ethine is 180 degrees, and the shape there is linear. Alkynes are the most reactive due to their high electron density. As a result of this, their pi electrons. Alkynes are the most reactive due to their high electron density as a result of their pi electrons. You can see the reactivity there. You see that the reactivity strength, you see the first molecular formula, the first general molecular formula refers to alkanes, the second refers to alkenes, and the third to alkynes. The arrow moving from the alkenes to the alkynes shows increasing reactivity. The next is synthesis or preparation of alkynes. The first method by which we can obtain alkynes is industrially from methane. You can obtain alkynes also from ethane, from methane. And the specific alkyne we can obtain from methane industrially is ethine. Now you can see there 2 molecules of methane in the presence of 140 degrees Celsius and 1 second. Those are the reaction conditions. It's going to yield us our ethine plus hydrogen gas given off. The next, also obtained industrially by the hydrolysis of calcium dicarbide. Now you can see from the reaction there, calcium dicarbide plus water is going to give us ethine plus calcium hydroxide. The next method of obtaining alkynes is by alkynes obtaining them from the laboratory is by dehydrohalogenation of alkyl halides or halogenoalkenes. If 1,2-dibromoethane is boiled with an alcoholic solution of potassium hydroxide, ethine is formed. You can see from the reaction there, 1,2-dibromoethane, in presence of alcohol and potassium hydroxide, is being boiled, is going to give us ethine plus 2 potassium bromide plus water. Thank you. We've come to the end of our lesson today. In our next lesson, we're going to be looking at the reactions of alkynes, and also we're going to look at how we can test for the presence of aliphatic hydrocarbons. How can you identify that this unknown compound given to you is an aliphatic hydrocarbon? And how can you identify that this aliphatic hydrocarbon is an alkane, alkene, or alkynes? Thank you, and see you next lesson.